So welcome back, guys, and yet again we're in the third lockdown, so I'm sorry you can't be with me in the lab, but I hope this makes up for the teaching that you won't be getting, and as ever I do hope you're keeping well and so are your family. So what we're going to look at now is the energy stored in capacitors. We've got to get capacitors to do some work, to do something for us. So when we feed energy into them from a power supply, what amount of energy goes into them so we can work out how much work they do when they're discharged, or the other way around, how much energy is stored in them within the electric field when they're charged up. So we'll remind ourselves that the charge on a capacitor is CV, and that means that the charge stored is proportional to voltage. So we'll set ourselves up a little circuit, and our circuit will look like this. Power supply and our capacitor. But what we'll do now is we'll keep the capacitor value fixed, but we'll turn the power supply up. Okay. Maybe I should have written that the other way around, but the point I'm making is what happens to the charge stored as we turn up the voltage, wait for a moment, turn up the voltage, wait for a moment. So we need to let the whole thing settle down. Okay, and this is something we could do practically. So what we could do is put 1 volt on the capacitor, disconnect the battery, and put a Coulomb meter across it, work out the charge, reset the Coulomb meter, turn up the voltage to 2 volts with the battery reconnected, disconnect the battery, 2 volt capacitor, how much charge is stored on it with a Coulomb meter, etc. Okay. Now, I did make the point there that you need to disconnect the battery when you connect the Coulomb meter. Otherwise, the Coulomb meter will start getting its charge from the battery. Okay. So what I do with students when they're here, of course, is I get the capacitor, connect it across a known voltage, and then put it across a Coulomb meter. Okay. Discharge everything. Get a new voltage, connect the capacitor in, count for a few moments, and then connect it across the Coulomb meter. And so we get some values of V, and we get some values of Q. Okay. Then what we do is we plot those values graphically. Don't worry about which way around I'm doing the axes here. It just makes the teaching easier. Okay. It's one of those weird things where you typically go for what voltage is needed for a known amount of charge, which is kind of a backwards way of thinking about it, but whatever. So this axis is going to be charge in coulombs. Okay, so this axis is a scale of Q, and the y-axis is going to be potential difference in volts. So this is a voltage axis. Okay. Well, it's sort of, kind of, I guess, what you'd expect happens. That if you have a small amount of charge, you only need a small voltage, more charge stored, more voltage. And if you remember, the capacitance, tells you something about the amount of charge stored per volt. Okay. So it's linear, as you'd expect. Now, remember, again, those of you that know me, I hate with a passion people who draw graphs where the gradient looks like 45 degrees, and all graphs have to be 45 degrees. No, they don't. It's just a good way to use the paper that we're drawing on. Okay, but it's important you understand that a bigger capacitor would store more charge for a given voltage, so would have a lower gradient. Okay, and a smaller capacitor would need more voltage to store the charge, so would have a higher gradient. Okay, but the main thing we can look at here is what's the area under the graph, and you'll see why I've done the graph this way around. So if we take a given voltage and we see how much charge is stored on that capacitor, we now ask ourselves, with this amount of charge stored and this potential difference across the capacitor, how much energy is stored on the capacitor? How much energy did it take from the power supply? And interestingly enough, it's this area under the graph. Well, if you look at it, it's VQ, but it's halved. Okay. I'm into FJ waffling mode, which is not brilliant physics, but isn't it interesting how a lot of formulae for energy stored have halves in them? Okay, a half QV here, okay, a half mv squared, a half ke squared for springs, etc. Okay, just interesting. So this area here is what we're looking at. Okay. Now, I need to justify to you that area is in the right units. Okay. So energy, the work done, yeah, on this graph is a half VQ. Typically, we actually write it a half QV, but never mind. Okay. So the units here are joules. Forget the half. The units here are joules per coulomb, and the units there are coulombs. So it's dimensionally consistent that a half VQ is the energy stored on the capacitor. So let's take this a little bit further. We've now got a formula for the energy stored on a capacitor, or the work done in charging a capacitor, and you can consider them to be 100% efficient. So when you connect a capacitor to an external circuit and discharge it, that will be the work done by the capacitor on the external circuit. We have the formula that the work done, or the energy transferred, is a half VQ. Okay, so that's one useful formula. Don't forget that Q, yeah, is equal to CV. Okay, and the other thing that's worth remembering is that if we rearrange this, V is equal to Q over C. So what we can do is we can substitute in and lose these letters, if you see what I mean. So what I'll do here is I'll get rid of that V first. So that V is Q over C. Okay, so the work done, or the energy transferred, is a half. Now V is Q over C, so Q over C times by the other Q. There we go. Okay, so we've shown where we've got a half Q squared over C from. Or another way of doing it is saying, and this is the one that we use more typically, this Q here is equal to CV. So we substitute in that Q for CV, but there's a V there already. So the work is a half. Okay, there's a V there. And that Q is, sorry, this Q here is CV. Okay, so we can write CV, but CV becomes V squared C. And the best way to write this formula is, I'll just put a slight dotted line through it. The best way to write it is a half CV squared. Okay, that's how we prefer to write it, in that sort of order. So you could put a capital E here, I suppose. It gets very confusing with the electric field, but the energy stored on a capacitor when it's charged to this voltage with that capacitance is this much. The energy stored on a capacitor when it has this amount of charge on it with this voltage across it is that value. They're very useful equations. So let's put all this together now in an example, and it's one of my favourites. It's one where I'm going to make masses and masses of assumptions. So if you're a real physicist watching this, you'll go, oh, what's he doing? But, you know, we're playing at it, so let's have a bit of fun. Okay, so what I want to do is I've got this really clever idea that when I have a battery-operated torch, now this tends to go back, in fairness, to the days when torches had little lamps in them rather than LEDs. And to be honest with you, use them for a couple of hours and they'd go flat. So I'm going to stick with that example, okay? You could do a battery radio or your mobile phone or anything like that. Okay, it doesn't really matter. The point is, if you have a torch and you have a battery in it, once the battery goes flat, you have to get rid of those batteries or recharge them, and the recharging takes like 2, 3, 4, 5, 6 hours. Why not use a capacitor? So why not get rid of the batteries, okay, and just have a capacitor? Because I told you that when you connect a capacitor to a power supply, if there's no resistance really in that circuit, it will charge almost instantly. So you could kind of plug in your torch when it's flat, and it would charge within very short space of time. Imagine that was a car, an electric car, and you could stick it in the plug-in, and the capacitors would go, right, yep, thanks, I've got my charge on board, disconnect me. Matter of fractions of a second. Okay, so it's possible, and I'll show you how it is possible, and then we'll look at some of the limitations. So we're over to the world of my dreadful drawing skills. Here's a lamp in a torch. Okay, and what we're going to do is we're going to connect that lamp up to a capacitor. So here's the capacitor. I'll just put it in the back of the torch, as it were, and I guess we need a switch to switch the torch on and off. There we go. Okay, so imagine the capacitor's charged, flick the switch, the light comes on, and all well and good. Okay, now there are lots of assumptions I'm making here, and we'll deal with those assumptions when you know a bit more about capacitors in a later video. Okay, now I need to charge up the capacitor, so I'm going to have a couple of wires coming out of here. And hey, it doesn't matter which is plus and minus, does it? Because normal capacitors work either way around. Obviously the dielectric in a electrolytic is a bit different, but let's not worry about that. Okay, and all of this sits inside your torch. Okay. I know I haven't drawn lenses and concave reflectors and all of that, but give me a chance. So, imagine you've charged up the capacitor and you switch on and you let the torch run until the battery goes, the capacitor goes flat as all of its charge has equalised out. So what you do is you plug it into a battery again, and we're up and running again. Very quick charging device. So let's see if we can get this to work. Well, to do this, let's consider a torch that uses a regular battery first to work out how much energy we need to make a torch stay on for a certain amount of time. Okay, so over here, what I'll do is I'll say we've got a 5-volt lamp. Now, guys, this is a real skill that I've got, okay, that you need to be able to estimate when you're a scientist. So it's no good saying, well, I've no idea what lamp it's got. What kind of lamp is going to be in a torch? Well, it's going to be about a 5-volt one, okay. What wattage is it going to be? Well, I don't know, so sensible value. Let's make it a 10-watt lamp. Okay, so we turn it on and it's giving out 10 joules per second, and the battery will flatten after a certain amount of time. Yes, it gets dimmer. Let's not worry too much about that. Some of you will be aware that certain batteries, like the ones in your mobile phone, tend to stay at the voltage for quite a long time and then just drop off instantly. Okay, let's go with that. Yep. So how long will it last for if it's a battery torch? Okay, so a battery. Well, I reckon a battery lasts approximately 2 hours. Don't argue with me. Yeah, I just made that up. If I leave a torch on for about 2 hours, that isn't an LED one. My head torch, when I was teaching Outward Bound and stuff, I got 2, 3, 4 hours out of it, kind of maximum, because it had a little lamp in it. Okay. Now we're immediately in the realms of, oh, don't do this. Yep, seconds. So 2 lots of 60 minutes of 60 seconds, so 7200 seconds. Okay. Now, how much energy does it need to stay on for 7,200 seconds? Okay, well, I hope you remember that power is energy or work divided by time. Okay, therefore, Yep. The energy stored in that battery before it goes flat, estimate, is equal to PT. Okay. And I've made the numbers fairly easy, as you can see. So the energy stored in the battery here, yep, will be equal to the power, which was 10 times 7200 joules per second. So there we go. The energy stored in the battery was 72,000 joules. So the energy in the battery before it flattens, I better remind us that's the battery, yeah, is equal to 72,000 joules. Yeah, lots of assumptions. But what we've got to do now is we've got to get a capacitor that we can connect to 5 volts that will charge up happily and store 72,000 joules of energy, and then we can just get rid of the battery and replace it with that capacitor. So let's do that next. Right, so we've worked out or estimated, it's a good skill to have, how much energy would be in a normal battery when it runs a torch from the start to going flat. So we've got to put that same amount of energy into a capacitor and work out what capacitance we need. Okay, so let's swap tack now and look at the capacitor that we need. Okay, well, we know the energy stored on a capacitor, I'll put W, the work, is a half. You pick the right formula that suits you, CV squared. Okay, now interestingly enough, we know the voltage here, we're going to use 5 volts. We know the work that we need to do, 72,000 joules. So we'll rearrange this for what capacitor do we need. Okay, so the capacitor, yeah, rearranging. Okay, that stays where it is. So the half goes over 2 times the work. Okay, V squared goes over as well. So over V squared. So that's our formula. So now let's put some numbers in. The capacitor value that we will need, I think some of you can see where this is going, is 2 times the energy we need to get out of it. Okay, divided by, now this is where I would always make a mistake. Yep, you can see the mistake I've made. Squared. Okay, so that's 25. You reach for your calculator and you find the capacitance you need will be a nice 5,760 farads. Okay. Now, I'm not even flinching when I say that. Some of you should be wriggling in your seats. Okay. Because if you write that down and then go, yeah, okay, no bother. So what you've done is you've replaced a battery in a torch with a capacitor, and you're happy to have a 5,760 farad capacitor. Okay, that is theoretically what you'd need, and it's a really good estimate, but that is absolutely flipping massive capacitance. Okay, I did a little quick thought about how that compared to capacitors we use in our laboratory. This is about 10 to the 7 orders of magnitude bigger than normal capacitors. Okay. In other words, this one here, okay, there's your D cell. This capacitor here is 4,700. Oh, well, that sounds about right. 4,000. No. 4,700 microfarads. Okay, so this is 4,700 millionths of a farad. Okay, so you can see where these sort of numbers come from. Okay, so yes, you could build it. Okay, and when we have more time and you were in the class with me, we'd work out how big this was, and then we'd work out how big this would have to be. And yeah, if you built it, fine, do it. Okay, but this capacitor would be kind of the size of my lab. Okay, so your torch would be lovely. It would last 2 hours, but you'd have to be hauling around this great supercapacitor behind you, okay, to get the torch to work. Finally, some assumptions. We'll learn later on that even this won't work because capacitors, as they discharge, lose charge, and if they lose charge, they lose voltage across them. So the lamp would get dimmer and dimmer and dimmer. Now, I haven't got it out here, not because I'm too lazy, but I want you to do something else. Okay, I'm going to put a link up in a second, and if you've got time, have a look at that link. I do own a very large capacitor, nowhere near this value, okay, but I do own a very large capacitor that came out of a uninterruptible power supply on a computer. Have you got it? The power supply to the computer is uninterruptible, okay, or it's interruptible power supply, which means you can disconnect the main supply and the capacitor goes, okay, I'll keep you going. I'll keep you going. And it's one, when you see how big it is, it's one of a massive bank of capacitors that were on this mainframe computer to keep it going when there was a glitch in the power supply. And it kept it going, I don't know for how long, but I mean, seconds, very short space of time. Because building large capacitors that will keep things going for hours is just not an option. Okay, so I'll put the link up to that video. I think you'll enjoy it because there's some seriously counterintuitive physics in it and some questions that I ask and ones that I hope you can answer. So I hope you found that video useful and you now feel you really understand energy stored on capacitors and the formulae that are used to calculate how much energy is stored on a capacitor. And if you had to, you could do some kind of estimate of what capacitance would be needed to replace a battery. Anyway, I'll be taking this topic further on, I hope, and making more videos, and I look forward to seeing you then.